Hello and welcome to Toddcast number 51. So continuing on with alcohol. So last one we talked, I'd say briefly, but it probably wasn't all that terribly briefly. But we talked about the alcohol functional group, hydrogen bonding associated with it, just recognizing its water solubility, boiling point, some of the other factors that came into play. Mentioned is a very common biofunctional group. So there'll be lots of interesting biomolecules that we'll be dealing with over the course of this chapter. But want to revisit stuff you already know. So that's actually a major part of OCHEM because it's cumulative. It builds on previous topics. They all integrate when you consider synthesis, when you consider how to convert one molecule into another. The changing one functional group into another is very, very common and important to remember just how we do it. So for alcohols, substitution, reduction, oxidation in some cases, are going to generate this functional group. We just want to make sure we have a good arsenal to begin with. So if you recall, you can do it by nucleophilic substitution. Note that this is a primary alkyl halide. Notice it's low temp. So because it's low temp, it's going to have a tendency to favor substitution over elimination. And you should also note that if it's primary, it's by way of an SN2 reaction. So SN2s are one way to make an alcohol. So here we're going to go from propyl chloride to propanol, and it's one propyl chloride to one propanol specifically. We can also do this at a tertiary or secondary carbon, choosing tertiary here. So here we have 2-methyl 2-chlorobutane, or I should say 2-methyl butane chloride. I don't know, whatever IUPAC name you want to use for it. The key thing is it's on a tertiary carbon this time. And tertiary, if you recall, is an SN1. SN1, I can get away with a little bit worse of a nucleophile because nucleophile isn't going to influence the reaction rate. Still has to wait till the chloride leaves. If the chloride leaves, you get a carbocation. And then that carbocation can get attacked by water, forming a hydrated butane. And then another water can come in and deprotonate that O and turn it into the alcohol we get up here. So long-winded SN1 process, but leaving group leaves, nucleophile attacks, and you deprotonate to get it back to a neutral state. Again, this is an SN1 reaction. May I also recall from the alkene chapter, you can add an OH to an alkene. You can do this either in a Markovnikov or anti-Markovnikov fashion. Here's my more crowded. Here's my more H side. So in this case, as you're probably hopefully saying in your mind, H goes where H is. So I'm not sure how I keep missing that thing, but H goes there, H goes on the more substituted, so H goes where H is. Markovnikov addition. You can also do anti-Markovnikov. Well, okay, you can, but I have one more Markovnikov with mercury. So using the mercury species, you can again add to this more substituted or more crowded carbon. And then BH3 hydroboration followed by peroxide workup, basic peroxide workup. You can have anti-Markovnikov addition. So nothing new, just revisiting. You can get it through substitution, SN2 or SN1, depending on the type of alkyl halide you start with, and then addition to an alkene. I drew terminal alkene. You can also do an internal alkene. And again, Markovnikov and anti-Markovnikov if you want to target where you want your OH. Okay, those reactions hopefully seem familiar. And then there was also one where we talked about how to make alcohols a better leaving group. So I want to revisit that exact same slide as before and remind you that if you add tosyl chloride, this OH can attack the tosyl group, attack that sulfur, kick out the chlorine. And so now you'll have the ROH TOS with a plus on the O and a Cl minus. Cl minus lone pair. Cl minus can come in and take that H and turn it into just an R O with the tosylate on it. Notice that because we reacted at the oxygen, because our nucleophilic attack was at an oxygen added to the tosyl, not at the carbon. So O, by going on to tosyl, the chirality of the R group, the one attached to the oxygen, was not impacted. So it starts S, it finishes S. We also can mesylate it. So mesyl chloride, very similar, except instead of a large benzene ring, it's a CH3 on the sulfate. So it's a little bit smaller, but still same result. You add it on, and because the O is attacking the mesyl, the chirality of the R does not change. You can also add SOCl2. This is a little bit different. Now the O is going to attack the sulfur, displacing the chloride, but the chloride can come in from behind, attack the R. So because this goes by an SN2 mechanism, we can only do this with a primary or secondary alcohol. And because SN2, we get inversion of chirality. That is assuming if OH is top priority and it's kicked out and replaced by a chloride, which becomes top priority, then you get inversion. S goes to R and R goes to S. PBr3, same story as we mentioned before. With instead of putting in chloride, we now have PBr3. It's an SN2 reaction where O first attacks the phosphate, displaces a Br. That bromide then can come in backside attack because SN2 with the R kicks out the O, and you turned it into an alkyl bromide. That is also an SN2 reaction. So just note that because these are SN2, you get inversion. And you get limitations of a primary or secondary carbon. Can't do this with tertiary. And then HCl, zinc chloride, just random thing, but you can also protonate this O, it leaves, and then chloride will come in. This basically just converts it into a racemic alkyl halide. Okay, so SN1 reaction. This is added, we didn't go through this on the previous one, but just so you know, you can do it with a tertiary as well, turn it into a chloride if you want to. But because it's tertiary, because it's an SN1 reaction, you can run the risk, well, not run the risk, but just the reality of converting from whatever chirality, S to racemic or R to racemic. You lose your chiral purity. HBr, same sort of thing. You can add the H here, tertiary, take it off. So that's also an SN1 reaction. So for the SN1 reactions, again, just note that you get racemic and that observe with tertiary. Okay, so you have these different reactions. So previously, we said you can still form an alcohol by way of an SN1 or SN2 reaction, depending on whether it's primary, secondary, or tertiary. You can also get it by addition, antimarkovnikov or Markovnikov. And we can also convert OH into different functional groups, different and better leaving groups. Retention of chirality, inversion of chirality, loss of chirality. Okay, I'm hoping that all those sound familiar. I introduced a couple new reagents and added a few stipulations, but you've seen it all. And my assumption is that will fall into place reasonably quickly. I want to add a couple bio examples. And in doing this, see if we can take our OChem knowledge and what we know what we know to happen in a flask, and see if we can figure out what actually happens inside a biological system. This carbon count, just want to do this real quick. This is 1, 2, 3, 4, 5, 6, 7, 8, plus 2 methyl, so 9 and 10. It's a category of compounds. We have 5 carbons, 10 carbons, 15. And if you see a commonality here, it's because I keep on adding 5 carbons. So these are what are known as terpenes. It's a class of biomolecules, natural products as we call them in OChem, that are made from this skeletal unit. Notice it is 4 carbons long, 1, 2, 3, 4, with a methyl on 2. So it's a 5 carbon species known as a terpene, where if, darn it, it's going the wrong way. There we go. So that'd be 1 terpene unit. That's another terpene unit. They are each 5 carbons, 5 here, 5 here, so for 10 carbons total. So we call it a monoterpene because it's 10 carbons. Introducing this, not that it's a main staple of what we're going to do in this class, nor honestly is it probably something we'll even bother testing. It's quite biological and quite a amount of trivia, which is something you should know. That naturally occurring fats you find in biosystems. One way to make a fat you're probably familiar with is using acetyl-CoA, a 2-carbon species, and adding it 2 at a time, making long chain fat. 2 plus 2 make for 4, plus another 2 for 6, another 2 for 8, another 2 for 10, and etc. Meaning a lot of our straight chain fats are 12, 14, 16, 18 carbons long. Arachidonic acid, which popped up real briefly when we talked about prostaglandin formation, that's a 20 carbon naturally occurring straight chain acid, or carboxylic acid. We also deal with fatty acids associated with the lipid bilayer. Those are almost exclusively in that 12, 14, 16, 18 range. They may or may not have pi bonds. The point is they're made by fatty acid synthesis, which is a long chain even number of carbons. The other lipids we have in our body are terpenes, 5 units multiplied together. So 5 and 5, or 5, 5 and another 5 make 15, so forth, where these may become interesting. When you talk about, for instance, hemoglobin, they talk about the 4 different groups holding the irons, the 4 different hemes. And I don't know if you've ever noticed or were taught, but they say 2 are alpha and 2 are beta. The difference between alpha and beta is a different terpene marker coming off of that heme group. And so that identifies what type of group it is and how it will bind with the rest of the, I guess, the structure of the protein. So just a little side note. So this is known as a terpene. I've gone off on yet another bio tangent that I will not test, but I think it's actually pretty interesting to toss in the middle of this. If you take this terpene and you add, this looks like a phosphate, but there's actually 2 of them. So I want to emphasize this nomenclature. It is a phosphate, but because it can give you a lot of energy, as you're hopefully aware, ATP and ADP have phosphodiester bonds or phospholinkage within a phosphate to phosphate. This is how we store energies. ATP is probably what you know for sure. And because it has this phosphate linkage, we call this a pyrophosphate. And so if you're aware, pyro meaning heat or burning, or I don't know what Latin for, but let's just say it's heat. It's a phosphate, a biphosphate or bisphosphate that can give you heat. So it's, if you will, I'm turning the OH into a better leaving group, just like we do in biomolecule, or in the previous slide, where we talked about turning it into OTOS or turning it into bromide or chloride. This is the same thing that happens biologically. The exception here, or the additional thing here, if you will, it's a better leaving group, but also it's an energizing leaving group. If we need the energy, we can hydrolyze here to push an unfavorable reaction. So making OH groups reactive, just like we did by tosylating it, we're now going to pyrophosphorylate it. Bad leaving group turned into a great leaving group that comes with a built-in energy supply. This is glucose. And just to make sure, this one is down, up, and down. So if you have carbon 2 down, carbon 3 up, and carbon 4 down, you match it to the fingers on your right hand. You'll notice if you're looking at your palm of your right hand, your thumb represents 1, your index finger is down representing 2, your third finger is up, middle finger up representing 3, your fourth finger is down representing this OH on carbon 4. Your pinky is down because that group is going down. That will match with a right hand to verify it's glucose. If you ever want to double check, match your fingers for mannose, glucose, galactose, something we mentioned in class. It'll pop up in one of the sugar lectures down the road, but hopefully you recall how that works. This group, this OH is up, or the CH2OH group is up or above the ring. This is below the ring. So revisiting something we had from cyclohexane, they're on opposite sides, up and down. So they are trans to one another. Because they are trans, we refer to that as alpha. So this is alpha D glucopyranose, or this is the alpha anomer of glucose. not a very leading group, but because it's on a bond with, or a carbon with two bonds to O, it's a little more reactive. I can turn this OH into a good leading group, just like I did here with a bad leading group, turn it into pyrophosphate. This one has the same pyrophosphate for energetic powering, but it also comes complete with a little more molecule dangling on to the end. So I take it from a bad leaving group, biologically, it now becomes a great leaving group. So it's interesting that a lot of the things we do in OChem as part of our overall synthetic strategy of building molecules, bio has already done it for us, or they've already done it, perhaps in a slightly different way, but they've done the same thing, make O better leaving group, but they've added a little stipulation that you can also do it with a pyrophosphate to make it energizable. I'm not sure if that's a word, but it should be. Same thing here, bad leaving group turned into a pyrophosphate, which means a good bulky leaving group that is energizable. Okay, another thing that corresponds to both bio and chemistry, so we'll say it's kind of a biochem topic, is paying attention to the oxidation states. So just revisiting, I want to just go through oxidation states real quick. Let's choose this molecule right here. If I have a hydrogen bonded to a carbon, another hydrogen bonded to the carbon, two bonds to O, you were probably taught oxygens are -2, H's are +1 each. So if you have two at +1 and another O at -2, so +2 and -2, that adds 0. So for the overall charge to be 0, carbon must be 0. Definitely works, but I have a better way that I hope you'll buy into. Take every bond and decide which atom is more electronegative. So in this carbon-hydrogen bond, if you recall, it is Fonck Ulrich, meaning O is more than C, C is more than H. So because C is more than H, I'm going to draw this bond with a negative on carbon, positive on hydrogen, negative carbon, positive hydrogen, meaning if this spontaneously broke into ions, it'd be H plus and C minus, H plus and C minus. Oxygen's more electronegative, so I put the negative on O. Now if I draw the individual circles, I have H as a +1 like I had there. I have oxygen as a -2 like I had there. And lo and behold, the carbon with a plus, a minus, and a minus adds up to 0, just like we had right there. So it's a kind of a new, and I guess it's similar to the mathematical way you took the central atom, figured out how many electrons it had, and then how many it lost to neighbors, and came up with some mathematical formula. I say forget the formula, just draw the structure and identify which charges, which electron distributions will go with a given atom. So let's go ahead and I want to try, let's say, this compound right here, because I'm not sure what that means. Just going to draw it out. I know it has a carbon-carbon bond. The O in parentheses means a carbonyl and two H's. So H is less electronegative than carbon. O is more. Carbon is the same as carbon. O is more. H is less. H is +1. O is -2 as expected. Each individual carbon is +1, +1, which is exactly what we concluded. So you can determine the oxidation state by just drawing the little circles around the various atoms. So let's do CO2, and I'm going to be done with it. Now, CO2 is a little more simple than the other ones because there's only two atoms. So if you have two O's at -2 each, that means -4. Carbon has to be +4, but I can still do the same thing. Minus, plus, minus, plus, plus, minus, plus, minus. O is -2, O is -2, carbon is +4. Okay. Practice with this. If it's new, you've never seen it before, it's a way to get oxidation states from structural perspective, and it's actually pretty useful. Okay. The other thing then, want to note, because H is less electronegative than carbon, it will always donate electron density to carbon. So carbon with a lot of H's will have a negative oxidation state. Carbon lots of oxygens will have a positive oxidation state. So oxidation, you'll notice, is the gain of O and the loss of H. In the other direction, reduction, red reduction, is the gain of H and the loss of O. So hydrogenation, the gain of H is reductive. Dehydrogenation, the loss of hydrogen, is oxidative. Gaining O's, oxidative. Losing O's, reductive. So notice the H count keeps on going down, or H's per carbon goes down, and the number of O's per carbon goes up as I go from the top of this chart to the bottom of this chart. Recognizing oxidation states is going to be incredibly helpful for a lot of the chemistry we'll do. So we're going to see alcohols being oxidized to carbonyls, which means they're going to go from, in this case, a -2 to a 0, or potentially from, in this case, it's a diol at -1 to a dialdehyde at a +1, or a dialdehyde to a diacid +1 to +3. So typically, every time you have the gain of a bond to O, it is coupled almost always with the loss of a bond to H. Lose a bond to H, you go up by 1 in the oxidation state. Gain a bond to O, you go up by another 1 in the oxidation state. So if I were to go from an aldehyde to a carboxylic acid, I gained a bond to O. I went from 2 bonds O to 3. I lost a bond to H. I went from 1 to 0, which means this should be oxidized by 2 electrons. Double check. 0 plus, plus, minus. This is +1. In the end, it is 0 plus, plus, and plus, +3. So sure enough, it works out that way. When you end up gaining a bond to O and losing a bond to H, you're oxidized by 2 electrons. So knowing this chart will help you see the big picture of functional group oxidation reduction. We're going to do an awful lot of this when we deal with alcohol and carbonyl chemistry. So carbon can take on a wide range of oxidation states, anywhere from -4 with all hydrogens to +4. And as mentioned, this is a huge part of chemistry and biology, coupled with the fact that nitrogen can also have this wide range. Nitrogen can go anywhere from -3 to +5. Because of its vast array of oxidation states, it is also really important in the bio scheme, although carbon is more important. Carbon molecules are typically what we oxidize and or reduce. So methane, start with methane. And again, we have a plus and a minus, plus minus, plus minus, plus minus, -4. So 0 H's, or I mean, excuse me, 0 O's, 4 H's. I'm going to skip down, as we mentioned, every time we gain a bond to O and lose a bond to H, we get oxidized by 2 electrons. So if I go to methanol from there, then I lost one of my bonds to H's, so I only have 3 H's, and I have 1 bond to O. And just double check, plus minus, plus minus, plus minus, plus minus, 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 and plus. So this is -2. So sure enough, it was loss of 2 electrons. When I go to this compound right here, now I have 2 bonds to H and 2 bonds to O. So I gained a bond to O and lost a bond to H. Just double checking, plus minus, minus plus, minus plus, minus plus. It's 0, just like we predicted there. This one was -2, just like we predicted up there. Again, if I lose an H and gain an O, so I go to this compound right here, this carboxylic acid. We already did this one earlier, but let me just do it again. Plus and minus, plus minus, plus minus, plus minus. Overall, there are 3 pluses and 1 minus. So this is in fact a +2. So 3 pluses and 1 minus is +2. And last but not least, we did carbon with 2 oxygens, carbon dioxide. It has 4 bonds to O, no bonds to H. So once again, it has gained a bond to O and lost a bond to H and gone to +4, which we evaluated earlier. So it's a kind of simple perspective that actually is incredibly powerful for watching redox chemistry happen in biomolecules and organic molecules. So this table, I don't know, use it as a guide. Just know what the oxidation states are of carbon. and how things change. And just note that when you gain bonds to O and lose bonds to H's, you've been oxidized. When you gain bonds to H and lose bonds to O, you've been reduced. So just like we said before, gain of H, went from 0 to 2 to 4, was reduction. Loss of O is also coupled with that. Going the other direction, gaining bonds to O or losing bonds to H is oxidation. It is information overload, but in such an organized fashion that hopefully it makes life a little bit easier. So the relative oxidation states, that little bit we just did, I hope it settles in and it seems kind of cool and you recognize this as a useful tip. But as soon as you can recognize redox chemistry in both OChem and bio, it will make a huge difference in how you're processing this. So I hope this went well. And as always, I will see you at the next podcast. So I'm signing off right about now. Bye.